Thermochemistry and thermodynamics are two topics that are related to each other, and both of them are dealing with energy. So, thermochemistry is part of thermodynamics, and that part of thermodynamics is related to heat transfer. And what that means is that when you have a process, physical or chemical, like for example, a chemical reaction or a compound being dissolved in water, you can have an amount of heat that is required for that process to happen, or an amount of heat that can be released when that process is happening. So everything that is related to heat transfer, amount of heat that is being used or obtained from a process, it's thermochemistry. And then thermodynamics, it's how the energy it's being converted into a different type of energy. So in the beginning of this topic of this discussion, we're going over some definitions, and you will see like how we have different types of energy and how those energies can be converted into a different type. So starting with the definition for heat, heat is a type or a form of energy, which means that sometimes when I am referring to heat, I might say energy, or sometimes for energy, I can use the word heat, depending on what I am discussing. So heat can be transferred. If you're looking at an object, it can be transferred from the object to another object or anything that is close to it, or from a substance. You will see that every chemical compound contains energy, and that energy can be transferred as heat also. The definition for energy is the capacity to do work, and energy is something that it's the only thing that is not classified as matter. And you need energy, or you can get energy from a process, chemical or physical process. So different types of energy I have here. Number one, kinetic energy. And kinetic energy is the type of energy that is associated with the movement of something. So when you have a substance at a microscopic level, the particles of the substance can be moving around. Depending on how fast those particles are moving, your amount of kinetic energy will be different. The faster the movement of your particles, the higher the amount of the kinetic energy. Now, a specific example of kinetic energy is thermal energy, which is the amount of energy associated with heat. Now, heat and temperature are not the same. Remember, temperature is a measurement. Temperature is the measurement that tells you how hot or how cold a substance is. So you can have an idea of how much heat a substance has based on the temperature, because heat and temperature are directly proportional. The same thing happens with kinetic energy. Kinetic energy and temperature, they are proportional. As you start increasing the temperature, the particles in a substance will start moving faster because they're gaining kinetic energy from the heat. The second type of energy that I'm going over is potential energy. And now potential energy is that type of energy that is associated to a position or a location. A specific example of potential energy is chemical energy, which is one that we're going to focus a lot during this topic. So chemical energy, it's the amount of energy that is associated with chemical bonds. When chemical bonds are formed, if it's a covalent bond like the one that I'm showing you here between H and Cl, that covalent bond, right, represents the sharing of electrons. Okay? So when your electrons are being shared between the H and the Cl, that bond has an amount of energy associated to it, which means that if you want to break that chemical bond, you need energy. When the chemical bond is being formed, an amount of energy is released. So you have a number right there, and there are tables with different types of chemical bonds and the amount of energy associated to that specific chemical bond. So that covalent bond that you have between H and Cl has an amount of energy of 431 units of kilojoules per mole. So every mole of HCl that you have contains 431 kilojoules of energy. So kilojoules, it's a unit of energy. So that's the next thing that I have here. Different types of units for energy. I have four different ones and you have the definitions in there, but mostly the ones that we use is joules and kilojoules. You will see that in the examples that I'm solving here today, the units that you have for most of them are joules or kilojoules. So that unit joules that we use, the abbreviation is just the letter J, is the unit for energy in the International System of Units. If you want to convert joules to kilojoules, the relationship between kilojoules and joules is that in every kilojoule you have 1,000 joules. So if you have a number that it's in units of joules and you need kilojoules, you will have to divide your number by 1,000 to get a new number in kilojoules. Now we have different laws of thermodynamics, and I'm going over the first one because that's the one that it's related to this part where I'm talking mostly about heat transfer. So the first law of thermodynamics, it's very similar to the law of conservation of matter. You know that matter cannot be created or destroyed. It can be transformed. So the same thing applies to energy, and that's the first law of thermodynamics. Energy is never created nor destroyed. It can be transferred, which is what we study in thermochemistry. Energy can be transferred from point 1 to point 2. It can be released, it can be absorbed, or energy can be transformed, which is what we study in that part for thermodynamics. So transform means that you can have chemical energy, okay? That this is an example. That energy that you have in the chemical bonds, when the chemical bonds are being broken to form new substances, an amount of energy might be released, and that amount of energy can be used to do some type of process like lighting up a bulb or using it as electricity. So the energy is being transformed because what you have in your chemical bonds now is your potential energy or chemical energy. Okay, and then that energy can be released as heat, as light, and that's a different type of energy now. Okay, if it's released as heat, what you have now is that thermal energy, which is a type of kinetic energy. So energy can be measured as an amount. That's what quantification of energy means. So we can actually measure how much energy you're getting from a chemical process or how much energy is being transferred when you have a physical change. We have different properties listed here, and these are thermodynamic properties, which are the ones that we're using to measure amounts. Okay, we have amount in heat, which we use letter Q, enthalpy letter H, entropy letter S, and Gibbs free energy letter G. We quantify this, especially the last three, not so much heat. Okay? The last three, we quantify them looking at a change. Okay? How much enthalpy you have, let's say, on the reactant side, and then how much enthalpy you have on the product side. The difference between the two will give you an overall amount of enthalpy. So we look at a final and an initial state to determine the overall amount for that specific process. So you will see that I will start using, instead of just the letter H, the letter S, the letter G, I will start using a triangle in front of those letters, meaning that we're actually looking at a change. Okay, so I will make a note of that later so you get to see what I'm referring to. Whatever we're looking at, a physical change, a chemical change, there's always a system and a surroundings. And these are just thermodynamics definitions. So the system, we define the system as whatever we're actually looking at. For example, if you're mixing hydrochloric acid and sodium hydroxide, right? That's an acid and a base, and what you have is a neutralization reaction. When you're mixing your reactants, right, to have your chemical reaction, that is your system. You want to know what's going to happen if you're mixing your acid and your base. So since that's what you're studying, that will be defined as the system. Now, everything that is around that system will be defined as the surroundings. For example, your hydrochloric acid and your sodium hydroxide are aqueous solutions. So that water that you're using as the solvent, or the solution where the actual reaction is happening, all of that is part of the surroundings. The beaker that contains the solutions that you're mixing, it's part of the surroundings. The table that you have, right, where you're placing your beaker, where the reaction is happening, the table, it's also part of the surroundings. So when we combine everything, the part that you're actually studying, that chemical reaction, with everything that is surrounding that chemical reaction, you have the universe. Now, this here is related to the first law of thermodynamics. The amount of energy of your universe, everything is constant. And what that means is that if your system is losing energy, that energy is not being destroyed. That energy will be transferred. It has to be transferred somewhere. Where? To the surroundings. Okay? If your system, for example, it's absorbing energy, that amount of energy that your system is absorbing will come from everything that is around it. If the amount of energy of your system is increasing, it means that the amount of energy of the surroundings will be decreasing by exactly the same amount. That's how the energy remains constant. Okay? If something is losing, something else has to gain the exact amount of energy that something was losing. I have a very simple example here, which is what I always use to go over this conservation of energy because it's very simple. So I'm giving you numbers. Everything that you have in there, it's given. Yeah, I'm not asking you to make up anything. So I'm going to show you transfer of energy. So I have my system, and let's assume that those numbers are in units of kilojoules, okay? Because I'm talking about amount of energy. So everything is in kilojoules. So my system, right, has an initial amount of energy of 6 kilojoules, and the surroundings, which is in contact with the system, has an initial amount of energy of 2 kilojoules. Now I'm moving to the second column where I have the change. The change is telling you by how much the initial amount is changing, decreasing by or increasing by. So I'm going to put an arrow telling you what's happening to that 2 that you have on that column for the change. So I'm going to say that the system has an initial amount of 6 kilojoules of energy, and now the change for that one is decreasing. So that initial amount is decreasing by 2 kilojoules. Okay? Based on the first law of thermodynamics, the system, right, it's losing 2 kilojoules of energy because that initial amount is decreasing by 2. If the system and the surroundings are in contact, the amount of energy is being transferred between them. So if the system, the amount of energy of your system is decreasing by 2, the amount of energy of the surroundings has to increase by the same amount. This is assuming that the amount of energy is being transferred entirely to your surroundings. So I have now that my initial amount of energy for the system is 6, and that amount of energy is decreasing by 2. So what that means is that now the final amount of energy for your system is going to be It's going to be 4. Okay? So initially you have 6. That 6 is decreasing by 2. So now what you have is 4. Looking at the surroundings, you have an initial amount of 2 kilojoules, and that amount is increasing by 2. Okay? So now the final amount of energy that you have for the surroundings is going to be 4. Okay? One is decreasing by 2, the other one is increasing by 2. So I want to check something here. Look, the initial amount of energy, remember, system plus surroundings gives you the universe. So system plus surroundings, that's your universe. So the initial amount of energy for your universe is 6 plus 2, which is 8. And now you get to see that the final amount of energy for the universe is 4 plus 4, which is also 8. So the initial amount of the universe, the final amount of the universe remains constant because the energy is being transferred from the system towards the surroundings in this case, right? Because the system is decreasing, the surroundings is increasing. But the net amount is constant. So that's what the first law of thermodynamics means. Now I want to go over something else. So we're looking at energy here. What I'm doing here can also be applied to specific thermodynamic properties like enthalpy, which we're going to define in a little bit. Entropy gives free energy. So I'm going to put my energy here. In front of energy, I'm going to put a triangle. That triangle means change. And that change is a change It's a difference between what you have at the end and what you had in the beginning. So when you have a delta or a change, what that is in this case, we're looking at energy. So final energy minus the initial amount of energy, that's going to tell you the change between your initial state and your final state, which is what we use with thermodynamic properties. We don't actually worry too much about what's happening in between that initial and the final state. And you will see why it's defined as a state function. So looking here at the energies that you have in the table, I'm going to calculate that change for the system and also for the surroundings, so separately. So for my system, I'm going to write down delta E sys for system. So delta E, so final amount of energy for your system, it's in the table, that will be 4. Okay? So that's my final energy for the system, 4 kilojoules. The initial amount of energy for your system is in the first column, initial E, which is 6 kilojoules. When you calculate that difference, that will give you negative 2 kilojoules. So now I'm going to do exactly the same, but for the surroundings. The final amount of energy for the surroundings is 4 kilojoules, and the initial amount of energy for the surroundings, it was 2 kilojoules, which means that now this one is giving you a positive number. Now, that negative number that we're getting for the delta E for the system, that negative number is not an actual negative number. We don't have negative amounts of energy, same way that we don't have negative masses. That negative is just telling you what's actually happening with the energy. So in this case, you can see that your final amount of energy, it's smaller than the initial amount of energy. You see, the final is for the initial amount was 6, so you will get a negative number when you calculate that difference. That negative number, what it means is that that system is actually losing or releasing energy. That's what the negative sign means. So we knew that just by looking at the table, because I'm telling you that the amount of energy on the system is decreasing by 2, right? If it's decreasing by 2, it means that that amount of energy is being transferred somewhere else. So the negative sign in a number that it's an amount of energy is just telling you that the amount of energy for that specific process is decreasing, because that amount of energy is being transferred somewhere else. Now I have my system and surroundings here. When you calculate the delta E, or the change in energy for the surroundings, you get a positive number. The positive number is telling you that the amount of energy is increasing. Your final energy now is larger than the initial. You have a final equals to 4 and initial equals to 2, so your final, your energy is increasing. And that positive number means that the surroundings are absorbing that amount of energy. So the system and the surroundings are in contact. The overall amount of energy of the universe remains constant, because your system is losing energy or releasing energy that the surroundings are absorbing. Now more definitions, and we already talked about some of them a little bit. So I've been saying process since the beginning, like you can have a physical process, a chemical process. So that's just how we describe a change on something. So you have two reactants initially, and then at the end you're getting your products. So what's happening between your initial reactants and your final products, that's a process. That's just an example. So if you change the temperature of something, like a very simple example, what I have listed there, if you have a liquid and you increase the temperature, now your liquid, it's you decrease the temperature, sorry. If you have a liquid and you're decreasing the temperature, your liquid will become a solid, right? If the temperature is decreased enough for your liquid to reach that freezing point, so it will become a solid. So you're changing temperature, and that change in temperature will be part of that process that is happening, the freezing of your liquid into a solid. Now, whatever state you have, if it's an initial solutions that you're mixing to get your chemical reaction, your initial liquid that you're freezing to get the solid, the state of those substances or objects can be described with state functions or thermodynamic functions, which are the ones that we're looking at. The last ones. I'm listing several state functions in there because there are properties listed here that we already know. We know about pressure, we know about density, we know about temperature, and we're going to keep using temperature in this topic a lot. We have new things like internal energy, which is just the overall amount of energy that you have in a universe. Enthalpy, Gibbs free energy, and entropy, which we already have listed before. So all of these amounts that we have here, we're going to use them as the change in enthalpy, the change in Gibbs free energy, the change in entropy. So we're not actually looking at H for enthalpy, we're actually looking at the change in enthalpy, the change in the Gibbs free energy, the change in entropy. So these are three state functions that we're going to use to quantify amount of energy. That's what we're doing. We're determining amount of heat that is being transferred from point 1 to point 2, and that's an amount. We're determining overall amount of energy that we can get from a chemical process, let's say as a Gibbs free energy, so that's a delta G, so it's a number. So quantification of energy using this, specifically these three properties here. I'm not going over anything related to internal energy. Something important, and I'm going to write down that here, Q, which is what we use to represent heat. It's not a state function. So state functions are properties that we can determine by looking at a final and an initial state without worrying about what's happening in between those two. So the amount of, let's say, enthalpy that a chemical reaction needs for that reaction to happen, if it's a measurement in kilojoules per mole, it doesn't matter what steps are happening in between your reactants and your products, that amount of enthalpy will be the same. That's what the state function means. So before we start going over those thermodynamic properties, let's go over heat and specific heat. These are like simple calculations and definitions. So we have already like the definition for heat. We went over heat in the beginning, but you know that it's an amount of kinetic energy. And that amount of kinetic energy is flowing because you have heat transfer. That's what we're studying, how an amount of heat is being transferred from point 1 to point 2. Now a new definition is specific heat, and we use letter CS for specific heat. You might have something a little bit different from that depending on the reference that you're using. So specific heat, it's there's the definition, and then I will explain the definition. Is an amount of heat that you need to raise the temperature of 1 gram. Okay, so we're comparing exactly the same amount of substance by exactly 1 degree, 1 Celsius degree. You can find these numbers also in kelvins. The difference is still 1 degree, so the numerical value is still the same. So the relationship between specific heat, mass of a substance, and temperature, you have a mathematical equation right there that relates all four things: heat, mass, change in temperature, because that's the delta, and the delta means a change in temperature. Final minus initial. So all of those properties are related by that chemical equation, or that equation that you have right there, mathematical equation. So I'm giving you a list of substances with their specific heat in units of joules over grams per Celsius degrees times Celsius degrees. So I have numerical values that I'm going to use to explain that definition that you have for specific heat. So I'm going to use my two pictures here. I'm going to add some information. Let's assume that this is 1 gram, and that right there, it's also 1 gram. This one right here is copper. This one right here is gold. So Cu and Au. Now, if you check the table, we have specific heat for copper 0.3885, specific heat for gold 0.130. So I'm going to put those numbers under my pictures here. So what those numbers are telling us, that's the specific heat for each one of them. What that number, let's look at copper first. It's telling you if you have 1 gram of copper, let's say at 20 degrees, at 20 Celsius degrees, and you want that temperature to go from 20 to 21. For that temperature to change just by 1 degree, 20 to 21, your copper needs to absorb 0.385 joules of energy. If it absorbs zero point 0.3, the temperature is not going to change. It will stay at 20. If you apply an amount of energy that is 0.386, that temperature will go from 20 to 21. Anything lower than 0.385 is not going to be enough to increase the temperature by 1 degree. Looking at the gold on the right side, same thing. For the temperature of gold, if you have 1 gram, we're comparing the same amount, because if you have different amounts, then the amount of heat that you need to increase the temperature will be different. So we're comparing the same amounts for both of them. If you're looking at 1 gram of gold also, and you want the temperature for that 1 gram to increase from 20 to 21, okay, Gold needs to absorb at least 0.130 joules of energy for that temperature to actually go up. If you apply an amount of energy that is 0.135, the temperature will increase from 20 to 21. Okay? It's enough to start changing that temperature. If you use an amount of energy that is lower than 0.30, the temperature is not going to change. Okay? So that specific heat, it's telling you the minimum amount of energy that 1 gram needs to absorb for the temperature to actually change. So I'm going to look at the one for water, which is the first one that you have listed on the table. It's the highest number right there, 4.184. So you get to see that the numbers are decreasing as we move down on the table. If you have 1 gram of water at 20 Celsius degrees and you want that temperature to change from 20 to 21, the water needs to absorb at least 4.184 joules of energy for that temperature to actually go from 20 to 21. Okay? So the larger the specific heat for a substance means that the more heat that substance will be able to absorb before the temperature actually starts changing. So the higher the specific heat, the more heat you need to apply for that substance to actually change in temperature. Now, looking at the whole table here, I'm looking at water first. The last one is gold with the smallest specific heat. So if you're using this list here, the substance that will absorb the maximum amount of heat before actually having an increase in temperature will be the water. It has to absorb 4.184 joules of energy or heat before it actually changes the temperature. In your list, the one with the smallest specific heat will be gold, which means that gold will absorb the smallest amount of energy or heat before the temperature actually starts changing. So the specific heat is very useful because we can use it to actually calculate amount of heat that a substance is absorbing or releasing. So we have this equation here that we're going to be using a lot. This equation has Q, which is heat, M, which is mass, Cs, which is your specific heat, and delta T, which is the change in temperature. So when you multiply the mass times the Cs times the delta T, you can actually determine an amount of heat. Depending on what's happening to the temperature, increasing or decreasing, right? It's a change. So you have final minus initial. So depending on what's happening to the temperature, you might get an amount of heat that is a negative number or a positive number. Now, I'm going to look here at physical changes first, but what I'm writing under, like about the enthalpy, this applies to physical or chemical changes. So I have my solid going to liquid, going to gas. So I'm looking at the arrows moving from left to right in my diagram. I'm just writing down the name for the process. From solid to liquid, that's melting. From liquid to gas, that's evaporation or vaporization. Now gas back to liquid, that's condensation. And all of these are physical processes. Liquid to solid, that's freezing. Now when a solid goes to a liquid, it's melting. For that to happen, the solid needs to absorb energy or heat. For a liquid to actually go to a gas, the liquid needs to absorb heat. So moving from left to right in this diagram, that's representing absorption of energy. Now moving in the opposite direction, a gas going to a liquid going to a solid. That represents releasing of energy. So when a liquid becomes a gas, it's absorbing a specific amount of energy. When your gas becomes a liquid, it will be releasing the same amount of energy. So what I have for evaporation and condensation, if you have a numerical value right there representing amount of energy, those two numbers for evaporation and condensation will be the same number, the same magnitude with different sign, because in one direction that amount is being absorbed, in the opposite direction that amount will be released. Now here, this has to be delta H. Okay? So the change in enthalpy. And now we have the definition for enthalpy. We have mentioned enthalpy before. It's a thermodynamic property. It's a state function. But now the actual definition for enthalpy. Enthalpy is an amount of heat. It's what it is. It's an amount of heat that we're measuring at constant pressure. When you have a process at constant pressure, we use that term isobaric. So that's just an amount of heat, what we have for enthalpy. The numerical value for enthalpy, remember, we're quantifying, actually determining a number. The numerical value for enthalpy can have a positive sign or a negative sign, depending on what's happening to the amount of energy, if it's being absorbed or if it's being released. Amount of energy absorbed represents an endothermic process. And remember, this is not just for these physical processes that I have right here. This also applies to chemical processes. So when you have a negative delta H, that represents an exothermic process. So you have heat absorbed when you have a change in enthalpy with a positive sign, and heat being released when you have a negative sign. So this is not just for physical changes, okay, or when you have a solid going to a liquid. This also applies when you have an actual chemical reaction. Your chemical reactions can be classified as endo or exothermic depending on what's happening to the amount of heat. If a reaction requires heat for that reaction to actually happen, it will be classified as an endothermic reaction. If you're getting an amount of heat from your chemical reaction, then that will be classified as an exothermic reaction. So I have some problems here, and I'm not going to solve the overall problem. I'm going to identify what you have, what you can calculate, and I'm going to write down the final answer. So you should solve your problem and then compare your number with the one that I'm giving you. So I'm going to identify the information that you're given in your problem. You're trying to calculate heat. That's what you want. Okay? And remember, heat is Q. So that's what you're trying to calculate, how much heat. How much heat is required to heat a 28.4 grams of ice from that temperature -2 to 20 degrees. So this number right here is the mass, and then this here is what you're using to calculate your change in temperature, which is the final minus the initial. If you want to calculate heat, you need to use your equation right there. So your delta T is final minus initial. So your final temperature, look, this is telling you from -2.0 Celsius degrees to 20 Celsius degrees. So the final temperature is 20, the initial temperature is -2. So use those two to calculate your delta T. Now, you need the specific heat. This is an ice cube, which is water. So your CS, you can find that number in the table that you have. You have the CS for different substances, and for water is this. And you have the mass right there. So you can plug in the mass, your CS, your change in temperature, and you can calculate how much is Q. And you should get something close to the numbers that I'm writing down here. I'm writing down a final answer in 3 significant figures because you have everything in 3 significant figures. Let's put this one with 3 significant figures to 2 point. -2.00 Celsius degrees. So everything is in 3 significant figures. So I'm writing down my final answer there in 3 significant figures, and the unit will be joules or kilojoules. You're calculating amount of heat, which is amount of energy. Okay? So we have unit of energy. That unit that you have in your final answer is coming from the unit that you have in your specific heat. The unit of grams that you have, it's canceling out. Your mass, it's in grams. Your CS is in joules over grams times Celsius. And your delta T, it's in Celsius. So you see how your units are canceling out? And the only unit that does not cancel out is the unit that you have for heat. Now let me see the next problem so I can identify things here. And this one, you have to actually use the table 1, which is the table where I'm listing your specific heats, the substance, and the numerical value. So I have here an amount that's mass. You have here a numerical value that corresponds to Q because absorbs that amount 1.43 times 10 to the third joules of heat. Okay. So that's amount of heat, which is Q. And then you're given the temperatures here to calculate your delta T. Now the problem is asking you for the specific heat. So what you're trying to calculate is your CS. And you have the equation there. You can use Q equals N times CS times delta T. You can solve for CS. It's the same equation. So you have the temperature that is going from 24.5 to 39.1. So your final temperature is 39.1. Your initial temperature is 24.5. So this is the I, this is the F. So you need to calculate CS. To calculate CS, when you're arranging your equation, that will be the heat divided by the mass times the delta T. When you're doing this calculation, put these numbers here in parentheses. You might get something different if you don't use the parentheses there. Now, besides calculating CS, the problem is asking you for the identity. So I'm going to give you a numerical value that you're going to get that will be the answer, but make sure that you solve the problem and compare your number. You should get something close to this number here. And the units are joules over grams times Celsius. You know how mass is in grams. This one here will be in Celsius, and the heat it's in joules. So those are the units that you have for your final answer. So now using that number, which is the one that you should get when you're solving your equation here, plugging in everything, you can go back to the table where you have the specific heat for different substances. You can compare your numerical value and you can find out which metal is the one that you have for this problem. So some important information that applies to everything, okay? Not just this final problem here, but I'm using this problem to show you the statements that you have in the beginning of this page. Heat is always transferred from the hotter object to a substance that is at a lower temperature. Okay? Something that is cold cannot transfer heat to something that is at a higher temperature. Hot coffee is hot, and the temperature in your hot coffee decreases over time because the hot coffee is releasing or transferring heat into the surroundings. Okay? These surroundings are not going to warm up the coffee because the coffee is at a higher temperature. That's an example of this heat transfer from a substance that is a higher temperature into a substance that is at a lower temperature. Now, the amount of heat that is being transferred is not it's not going to that heat transfer is not going to happen forever. There's a point where the heat transfer is going to stop. If heat is being transferred between two substances that are at different temperatures, that heat transfer is going to happen until both substances are at the same temperature. That is thermal equilibrium. The temperature remains constant. There's no more heat transfer. If you have two objects, object 1 and object 2, object 1 is at a higher temperature. If you put both of them together, okay, object 1 at a higher temperature is going to transfer heat to object 2 that is at a lower temperature. Now the temperature for object 1 is going to start decreasing. As the temperature in object 2, it starts increasing. Okay? So one is decreasing, the other one is increasing until both of them are at the same temperature. That temperature right there represents thermal equilibrium. There's no more heat that can be transferred because now both objects are at the same temperature. So I have here a problem, and it's a long problem because we can get a lot of information from it. This is a problem about heat transfer until thermal equilibrium is reached. So I'm going to identify several things in your problem. I have two substances, silver and coffee. That's what you have. So for everything related to silver, I'm going to use one color. For every number that is related to the coffee, I'm going to use a different color. So I'm going to mark everything for silver. Actually, let's use the yellow. And now I'm going to mark everything for coffee. I have a mass of coffee, initial temperature for coffee, and I'm missing information here. This is part of your problem. That's part of the problem. It's just that I forgot to write it down. So that will be another piece of information that is for coffee. So let's go over the problem. Now I have identified my numbers, but let's go over the problem. You have a silver spoon and you have the specific heat for silver. You don't know the mass of your silver spoon. So that's what we're trying to calculate. Your silver spoon is at the initial temperature of 18 Celsius degrees. Now, you have your spoon at that temperature and you're placing the spoon inside of your cup that has 83 grams of coffee, and the initial temperature of your coffee is 35 degrees. Now, you have your spoon inside of your coffee and heat is going to be transferred. Heat is going to be transferred from the hot coffee at 35 to the silver spoon at 18. Remember, heat transfer always is going to happen from the hotter object to the substance that is at a lower temperature. So your coffee is initially at 35, the silver spoon is at 18, so your coffee will be transferring heat to the spoon. That's what's happening in this problem. Now, the problem is telling you when the two substances are at thermal equilibrium. Okay? So the coffee is transferring heat to the silver spoon. The temperature of your coffee will be decreasing because it's the one that is losing heat. The temperature of the spoon will be increasing because that's the one absorbing heat. So that transfer of heat will happen until the temperature is 33.8. That's what the problem is telling you. So that's a final temperature, which is the temperature when thermal equilibrium is reached. And that temperature means that the temperature of the hot coffee at 35 went down to 33.8. The temperature of your silver spoon went from 18 to 33.8. So now you have the spoon and the coffee at exactly the same temperature. That temperature right there, it's a final temperature for the spoon, and it's also a final temperature for the coffee. So I have both colors for that one because when you reach thermal equilibrium, both substances that are in contact with each other will have exactly the same temperature. And this is assuming that not heat is being transferred to the mug or everywhere else. Heat is being transferring from the coffee to the spoon, and that's it. So now I want to see what can I calculate with the numbers that I have. And this is heat transfer, so easy part is that we have only one equation. This is our equation. You're trying to calculate the mass of the silver spoon. That's what the problem is asking you. No. Unknown mass, and you're trying to find what is the mass of the silver spoon. So Q for silver will be equal to the mass for silver. Remember, silver symbol it's Ag, times Cs for silver times delta T. If you want to calculate the mass for silver, you do have the specific heat for silver. It's right there, and if you don't have it, you can use the table and find that value. The delta T you can calculate. Your initial temperature for silver is 18. Your final temperature for silver is 33.8. So you can actually calculate this one, 33.8 minus 18.0. So you can get a delta T. You have a CS. You want to find out the mass, but you don't have an amount of heat for silver. For you to calculate the amount of heat that silver is absorbing in this case, and you know it's absorbing because the initial temperature for the silver is lower than the initial temperature for the coffee. So for you to calculate that amount of heat for silver, you need the mass. For you to calculate the mass, you need the heat. So you cannot get the value of the mass of the spoon because you don't know how much heat the spoon is absorbing. So, okay, I'm going to keep that equation there, and then I'm going to see what I have for the coffee. Same equation. So for the coffee, you have a mass that's 83.0 grams of coffee right there. The problem is telling you that the CS for coffee, just to assume that is the same as the CS for water, 4.184 joules over grams times Celsius. So you have a mass, you have a CS. The change in temperature for the coffee, let's go back to the problem. You have an initial temperature of 35, a final temperature of 33.8. So you can calculate a delta T. And all of this is for the coffee. So I'm going to put 83.0 times 4.184 joules over grams times Celsius times delta T, which is your final temperature minus the initial. 33.8 is the final, which is the temperature at thermal equilibrium, minus my initial, which was 35.0. So with the numbers that you have in the problem for coffee, you can actually calculate the amount of heat that the coffee is losing. Remember, heat transfer from hotter object to cooler substance. The hotter one in this case is the coffee. So the coffee is the one that is going to be losing heat. And you can determine that by looking at the change in temperature. The temperature of your coffee initially is at 35, and the temperature is going down to 33.8. So the coffee is actually losing heat. It's losing heat because the temperature is decreasing. So my amount of heat for the coffee, we are expecting a negative number because the amount of heat is decreasing. So I have a negative number 417 joules. A negative number because that number represents the amount of heat that the coffee is losing. The initial temperature is 35, it's going down to 33.8, which means that the coffee is losing heat. The coffee is losing heat because that amount of heat is being transferred to the silver spoon. Now, the silver spoon is going to be absorbing heat. If you have your two substances in contact, the coffee and the silver spoon, the coffee is releasing 417 joules of energy. That means that if no heat is being transferred anywhere else, to the cup where you have the coffee, to the table, anywhere else, the heat is being transferred from the coffee to the silver spoon. If the coffee is losing 417 joules of heat, the silver spoon will be absorbing 417 joules of energy. Why is this information here important? When you go back to your problem, we initially wrote down the equation to find out heat for silver. We didn't have a mass for silver because that's what we are actually trying to find out. You cannot get the mass of the silver without knowing how much heat the silver spoon is absorbing. You do have ACS. You can calculate the delta T because you have a final and initial temperature for the silver, but you didn't have the mass to get the heat, you didn't have the heat to get the mass. But with the information that you're given for the coffee, you can actually calculate how much heat the coffee is losing. Since the heat is being transferred from the coffee to the silver spoon, now you know how much heat the silver spoon is actually absorbing for that temperature to change from 18 to 33.8. So with the amount of heat that the silver is absorbing, which is the same amount of heat that the coffee is releasing, you can go back to your initial equation and you can calculate the mass of the silver spoon. So you have the value of Q that you can plug in your equation and you can solve for the mass of silver. And let me get a number, which is your final number. That's the answer, but make sure that you solve the problem and that you get this number here. So you should get something close to 113 grams. So that will be the mass of your silver spoon. That silver spoon with a mass of 113 grams is going to be absorbing 417 joules of energy or heat that are being transferred from your hot coffee into the silver spoon.